Industrial automation is entering a new phase. AI is moving beyond dashboards, analytics, cloud reports, and passive monitoring. It is entering advisory systems, operator assist layers, predictive maintenance, advanced process control, digital twins, and agentic AI workflows that can observe, reason, recommend, escalate, and in limited cases, execute approved actions. For design engineers, automation engineers, AI engineers, control system engineers, manufacturing teams, project engineers, and operations leaders, this is not just a technology trend, it is an automation architecture shift. But the core mistake is this: AI will not replace control fundamentals. AI can enhance control systems, but it cannot compensate for poor loop design, wrong controller selection, weak instrumentation, bad tuning, missing fallback logic, poor actuator sizing, noisy measurements, or misunderstood process dynamics. If the base automation layer is weak, AI does not make the plant intelligent. It only scales weak decisions faster. That is why basic control algorithms still matter. On-off control still matters. Proportional control still matters. Integral control still matters. PI control still matters. Deadband still matters. Anti-wind-up still matters. Fallback logic still matters. Instrumentation still matters. Operator behavior still matters. Safety boundaries still matter. These are not outdated concepts. They are control behavior foundations. Every controller has a behavior profile. On-off control is simple, rugged, and decisive, but it cycles around the set point. Proportional control is responsive, but it usually leaves offset. Integral control removes offset, but it can be slow, unstable, or vulnerable to wind-up. PI control balances response and accuracy, but it can still oscillate, saturate, overshoot, or become sluggish when poorly tuned. No algorithm is good or bad in isolation. It is good or bad in context. A controller that works in a slow thermal process may fail in a fast flow loop. A deadband that protects a relay may create unacceptable product variation. Integral action that removes offset may become dangerous when actuator limits are ignored. An AI recommendation that improves energy efficiency may be unacceptable if it pushes the process near a safety, quality, or equipment constraint. Automation excellence is not about using the most advanced algorithm. It is about using the right control behavior for the right process at the right risk level with the right fallback. The future is not AI instead of control. The future is AI-enhanced control deployment. That means AI identifies loop degradation, predicts actuator wear, detects abnormal oscillation, recommends tuning review, supervises fallback modes, analyzes deadband behavior, monitors integral wind-up, validates controller performance, and supports better decisions before the plant enters instability, downtime, quality loss, energy waste, or safety exposure. The better engineering question is no longer only, which controller should I use? The better question is, what behavior does this process require under normal, abnormal, degraded, and emergency conditions? A controller is not just a formula, it is a behavior pattern. It reacts to error, noise, delay, actuator limits, process lag, load change, startup, shutdown, manual mode, saturation, and abnormal operation. If you understand that behavior, you can deploy control intelligently. If you do not, you may build a system that looks correct in documentation but behaves poorly in the plant. This becomes critical when AI enters the environment. AI can detect patterns, forecast failures, optimize set points, prioritize issues, and recommend actions. Agentic AI can go further by planning tasks, coordinating workflows, checking conditions, escalating issues, and triggering predefined actions. But AI needs a reliable automation foundation. Without that foundation, AI becomes a sophisticated layer sitting on unstable logic. Do not use AI to hide poor loop design. Use AI to expose it. Do not use AI to bypass past process understanding. Use AI to deepen it. Do not use agentic AI to randomly intervene in control systems. Use it within clear authority limits, fallback rules, approval workflows, simulation checks, audit trails, and safety constraints. The goal is not blind autonomy. The goal is controlled autonomy. On-off control is the most basic form of control. The output is binary. The final element is either fully on or fully off. There is no throttling, no gradual modulation, and no proportional balancing. That simplicity makes it rugged, inexpensive, maintainable, and useful in the right applications. You see on-off control in solenoid valves, electric heaters, relays, pumps, compressors, tank filling systems, permissive logic, safety cutoffs, interlocks, and emergency shutdown actions. Its strength is clarity. Its weakness is cycling. The process variable does not settle exactly at set point. It moves around it. The cycling amplitude and frequency depend on dead time, inertia, capacitance, sensor location, actuator response, load behavior, and deadband. Deadband is therefore critical. Without deadband, the controller may switch too frequently, causing relay chatter, actuator wear, valve stress, motor starts, compressor short cycling, heater fatigue, nuisance alarms, and unstable operation. With deadband, switching frequency reduces because the output changes only when the process variable crosses a defined band. But deadband is a compromise. Too wide and control becomes loose. Too narrow and switching becomes excessive. Deadband is not a casual setting. It must reflect process inertia, acceptable variation, actuator life, equipment protection, product tolerance, and operational risk. Common on-off failures include excessive cycling, wide process variation, nuisance switching from noise, poor sensor location, oversized actuators, and use of binary control because it is cheap rather than technically suitable. Corrective actions are direct. Design deadband properly, validate measurement, use filtering, debounce logic, confirmation timers, or voting where required. Protect actuators with minimum on-time, minimum off-time, anti-short cycle logic, and start limitation logic. If a loop cycles too often, stays stuck in one state, or fails to create expected process response, generate diagnostics and escalate it. AI can enhance on-off control by monitoring switching frequency, detecting abnormal cycling, identifying actuator degradation, and correlating cycling with downtime, energy use, product rejection, maintenance history, leakage, fouling, sensor noise, or changing load. Agentic AI can compare repeated switching against historical behavior, evaluate whether deadband remains suitable, create maintenance notifications, recommend solenoid inspection, suggest deadband review, or escalate the loop for engineering analysis. But AI must not casually modify safety trips, emergency shutdown functions, or protective interlocks. It may advise, diagnose, audit, and support root cause analysis, but deterministic safety logic must remain protected, validated, and independently tested. Proportional control moves beyond binary action. Instead of switching fully on or off, output changes in proportion to error. Larger error produces stronger correction. This gives smoother control, reduces harsh cycling, and supports better balance between supply and demand. But proportional control has a built-in limitation: offset. A proportional-only controller usually stabilizes with steady-state error. The process may become stable, but not exactly at set point. It reaches a balance point where controller output and process demand match, but that point may sit away from target. That may be acceptable for surge tanks, rough pressure control, low precision mixing, and systems where small deviation is tolerable. But if exact set point maintenance is required, proportional-only control is not enough. Key failure potentials are permanent offset, excessive gain, oscillation, overshoot, wrong bias, frequent manual correction, nonlinear process behavior, and gain values that work in one operating region but fail in another. Corrective action starts with one question: is offset acceptable? If zero steady-state error is required, proportional-only control is not the final solution. Then tune gain correctly. Use enough gain for meaningful correction, but not so much that the loop becomes unstable. Review bias so the controller operates around the correct baseline. Use gain scheduling where process behavior changes across operating ranges. Upgrade to PI control when offset cannot be tolerated. AI can improve proportional control by detecting recurring offset, comparing deviation with quality limits, identifying frequent manual bias changes, and separating tuning issues from actuator problems, sensor noise, or process disturbances. Agentic AI can run a structured diagnosis, detect offset, check persistence, compare against limits, review operating conditions, inspect actuator movement, evaluate gain behavior, and recommend retuning, bias adjustment, or migration to PI control. Integral control exists to remove steady-state error. Where proportional control reacts to current error, integral control accumulates error over time. As long as error exists, integral action continues adjusting output until the error is removed. That makes it powerful. It eliminates offset and automatically adjusts output to match process load. But it also introduces risk. Integral control adds lag. It can be slow, it can wind up, it can overshoot, it can destabilize the wrong process. Integral-only control is rarely the best general-purpose answer. It may suit slow, stable, buffered processes where precision matters more than speed, but in fast loops, noisy environments, actuator-limited systems, or integrating processes, it must be handled carefully. The biggest failure is integral windup. If the actuator reaches its limit but error remains, the integral term can keep accumulating correction. When the actuator becomes effective again, the stored integral action can drive the process too far, causing overshoot and long recovery. Other failures include sluggish response, hunting, poor behavior in non-self-regulating processes, and accumulation caused by noisy measurements or transmitter errors. Corrective actions are essential. Use anti-windup protection. Configure output limits correctly. Tune integral action based on process gain, dead time, and process speed. Handle manual to auto transfer carefully. Protect measurement quality with filtering, validation, and transmitter health checks. AI can detect windup risk by monitoring sustained error, output saturation, valve position, actuator response, and recovery behavior. It can identify loops that repeatedly hit limits and recover poorly. AI can also detect whether integral action is too aggressive or too weak by comparing overshoot, settling time, accumulated error, and disturbance response across operating conditions. Agentic AI can investigate repeated saturation with useful questions. Is the actuator undersized? Is the valve sticking? Is the set point unrealistic? Has load changed? Is the integral time wrong? Is anti-windup missing? That is practical AI-assisted engineering. PI control combines proportional and integral action. The proportional part responds immediately to error. The integral part removes remaining offset over time. This balance makes PI control one of the most widely used strategies in industrial automation. It is common in flow, pressure, temperature, and level loops. It is often simpler and less noise sensitive than full PID because it avoids derivative action. But common does not mean automatically correct. PI control can fail when process dynamics are ignored. Too much gain creates oscillation. Too little gain creates sluggish control. Too much integral action creates overshoot. Too little integral action leaves slow correction. Actuator saturation creates windup. Noise creates unnecessary movement. Loop interaction spreads disturbances across the plant. A PI loop tuned during commissioning may not remain suitable after equipment aging, recipe changes, production rate changes, fouling, valve wear, sensor drift, or process modification. This is a major plant weakness. Loops are tuned once and ignored for years. Then operators shift to manual, alarms multiply, quality variation increases, energy use rises, and maintenance costs climb. Corrective actions are clear. Tune based on process dynamics, not guesswork. Understand process gain, dead time, time constant, actuator behavior, and measurement quality. Configure anti-windup. Track oscillation, saturation, valve travel, slow recovery, and persistent deviation. Review operating envelopes. Use gain scheduling or adaptive tuning where required. Analyze loop interaction because loops rarely operate alone. A pressure loop can affect flow. A temperature loop can affect composition. A level loop can disturb downstream stability. AI can continuously monitor loop health and identify oscillating loops, sluggish loops, saturated loops, noisy loops, abnormal valve travel, and loops drifting from historical baseline. If a loop used to settle in 5 minutes and now takes 15, AI can flag degradation. If valve movement increases without process need, AI can suggest stiction or tuning issues. If output saturation becomes frequent, AI can check whether the process is operating beyond design limits. Agentic AI can detect the issue, collect relevant data, classify the pattern, compare it with known failure modes, recommend corrective action, create a maintenance or engineering ticket, and track resolution. In mature systems, AI may recommend tuning changes. In tightly governed systems, it may apply low-risk changes only after simulation, approval, validation, and restricted operating windows. That is the realistic path to AI-assisted control engineering. The hidden weakness in modern automation is over-automation without behavior understanding. A plant may have advanced PLCs, DCS, SCADA, historians, cloud analytics, digital twins, AI models, dashboards, and polished operator graphics. But if the engineer does not understand loop behavior under disturbance, saturation, noise, dead time, startup, shutdown, manual mode, degraded operation, and abnormal conditions, the system remains fragile. Many automation failures come from simple causes. A sensor is placed where it sees the process too late. A valve is oversized. A pump starts and stops too frequently. A deadband is copied from another project. A PI loop is tuned once and never reviewed. A set point is changed without downstream understanding. An alarm is added instead of correcting the control problem. A manual workaround becomes normal operation. An AI model is trained on data from a poorly controlled process. That is not digital transformation. That is automation debt. Before deploying Agentic AI, ask, is this plant behavior worth automating further, or does it first need correction? AI deployment must begin with controlled discipline. If the base layer is poor, AI analytics can produce attractive but misleading conclusions. The AI may detect patterns, but those patterns may only be symptoms of bad engineering. So where should Agentic AI help first? Start with loop health monitoring. AI can monitor thousands of loops and classify oscillation, deadband cycling, proportional offset, integral wind-up, sluggish PI response, saturation, valve stiction, sensor drift, and abnormal manual intervention. This matters because plants often have too many loops for engineers to review manually. AI can prioritize the loops that actually need attention. Next is fallback mode supervision. Many systems have fallback logic, but few teams monitor whether fallback has become normal behavior. A controller shifts to manual. A valve stays at limit. A loop operates in override. An interlock activates repeatedly. A bypass becomes permanent. Agentic AI can detect when fallback behavior becomes routine. That is a warning sign. If a plant repeatedly depends on fallback logic, the base control strategy may be weak, equipment may be declining, or the process may be operating outside its envelope. Next is control mode recommendation. AI can help evaluate whether a loop should remain on-off, proportional, integral, PID, cascade, ratio, override, or advanced control. It can assess process behavior, precision needs, actuator capability, load variation, and historical performance. AI should not replace engineering judgment. It should reduce analysis time and expose patterns engineers may miss. Next is predictive maintenance integration. Control behavior often reveals equipment health. Excessive valve movement, delayed response, frequent saturation, increased cycling, and abnormal control effort can indicate mechanical degradation before failure. AI can connect control behavior with maintenance records, vibration data, energy use, quality deviations, and downtime. That creates better asset intelligence. Next is operator decision support. Operators often see symptoms before engineers see reports. AI can translate control behavior into useful guidance, not another alarm, a practical advisory. This loop is oscillating. Valve output is cycling faster than normal. Process response is delayed. Similar past events were linked to valve sticking. Recommended action: inspect during the next maintenance window. That is useful. Next is simulation before action. Agentic AI should connect to simulation and digital twins wherever possible. Before recommending a tuning change, set point shift, or operating strategy, the AI should test the likely effect. Simulation does not remove risk, but it improves discipline. Next is documentation and knowledge capture. Many teams lose the reasoning behind control decisions. Why was this loop on-off? Why was this deadband selected? Why was PI tuning changed? Why was this fallback added? What constraints must never be violated? Agentic AI can preserve this reasoning, which becomes valuable when original engineers leave, systems are modified, or operations inherit logic without context. But some areas must stay tightly controlled. Safety instrumented functions, emergency shutdown systems, critical interlocks, burner management systems, high-integrity pressure protection, and machine safety functions should not be casually modified or overridden by AI. AI may monitor, audit, analyze repeated trips, support root cause analysis, and recommend engineering review. But safety functions must remain deterministic, validated, tested, governed, and independent. Direct set point optimization is another risk area. AI may recommend set point changes to improve energy, throughput, or quality, but those changes must respect operating limits, equipment constraints, product specifications, downstream stability, and safety margins. The danger is not that AI becomes too intelligent. The danger is that AI receives authority without enough process context. An AI model may optimize one metric while damaging a pump, stressing a valve, increasing fouling, narrowing safety margin, or creating downstream instability. That is not intelligence. That is uncontrolled optimization. So do not start by asking, where can we add AI? Ask, where does our current automation system lose awareness? It loses awareness when loops drift slowly, operators compensate manually, actuators degrade gradually, tuning becomes outdated, alarms repeat without root cause resolution, fallback modes become routine, process behavior changes after modification, and documentation no longer matches reality. That is where AI belongs first. AI should improve awareness before autonomy. A practical agentic AI model has 6 layers. Layer 1, observation. AI reads historian data, alarms, events, controller modes, output saturation, valve movement, set point changes, operator actions, and maintenance signals. Layer 2, diagnosis. AI classifies behavior as oscillation, offset, wind-up, deadband cycling, sensor drift, actuator stiction, sluggish response, process disturbance, or abnormal manual intervention. Layer 3, recommendation. AI suggests tuning review, deadband sensor inspection, valve maintenance, anti-wind-up configuration, alarm review, or process investigation. Layer 4, workflow. AI creates a maintenance ticket, engineering review task, operator advisory, or management report. Layer 5, supervised execution. For low-risk approved cases, AI may apply changes within predefined limits and only after validation. Layer 6, governance. Every recommendation and action is logged, reviewed, measured, and improved. That is how agentic AI becomes industrially useful, not as an autonomous plant brain, as a disciplined engineering co-pilot. The real future is control systems that explain themselves, not just trends, actual interpretation. This loop is oscillating with a 14-minute cycle. Valve output is moving above historical baseline. Process response is delayed compared with last month. The loop entered saturation 6 times in 24 hours. The behavior resembles previous valve stiction cases. Recommended action, valve inspection and PI tuning review. Risk level, moderate because the loop affects product temperature stability. Priority, before the next production campaign. That is, engineering intelligence. The automation world is not moving away from fundamentals. It is returning to fundamentals with more awareness. AI does not remove the need for strong control engineering. It makes strong control engineering more important, because when AI begins observing, recommending, or acting inside an industrial environment, every weakness in the base control structure becomes more consequential. The best automation engineers of the next decade will not be those who blindly adopt AI. They will be those who understand plant behavior deeply enough to deploy AI safely, practically, and profitably. The best AI engineers in manufacturing will not be those who only understand models. They will be those who understand controllers, actuators, sensors, alarms, process dynamics, safety logic, maintenance behavior, and operators. The best design engineers will not be those who only produce control architecture drawings. They will be those who design for normal operation, abnormal operation, degraded operation, fallback behavior, recovery behavior, and AI-assisted decision-making from the beginning. The future is not AI versus automation. The future is automation made more aware, diagnostic, adaptive, and accountable through AI. But the foundation remains the same. Understand the process, select the right control behavior, design the fallback, protect the plant, respect the operator, preserve safety boundaries. Then let AI enhance the intelligence around it. AI will not save weak automation, but strong automation, enhanced by disciplined AI, can transform plant operation, engineering decisions, failure prevention, reliability, safety, and performance. If this made you rethink control systems, AI, and agentic AI in real plants, get in touch and share your view in the comments. Are teams using AI to solve real control problems or decorating weak systems with advanced tools? Like, share, and subscribe to the channel for practical, sharp, no-fluff conversations on automation, control systems, AI, engineering management, and industrial intelligence. Follow me on LinkedIn newsletter for deeper engineering breakdowns, practical frameworks, and direct discussions on where industrial automation is really heading.